Something that's never sure how totally to do it, because when we talk about interesting molecules or interesting applications, the two things that students want to know is how important is this, and actually it's only one thing because they want to know, is that going to be on the test? Presumably the question, is that going to be on the test, is related to this anxiety you have that when I draw a molecule, you're supposed to have memorized its structure. And I've never told you to do that. But as we talk about applications of chemistry and how it affects your real life, we've already done some of this so far, but we'll continue to do it. The general standard is you don't need to memorize structures, but when you go to take the test, it's useful if you make it appear to me as though you were in class that day paying attention, okay? So some of you who took 351 for me know of a famous question on the first exam, which was, which of these compounds smells like banana? And some of you were so mad at me about that because you're like, I didn't know I had to memorize that. And others were like, yay, I thought that was interesting and I remember that. Try to be curious. And again, try to make it appear as though you were in class paying attention. Okay, so the subject of chapter 15 is carboxylic acids. I want to show you the structures of a few that are relevant biologically and that some of us maybe take in order to function in our daily lives. So here is a famous carboxylic acid. You have heard of it before. It's called acetyl salicylate or acetyl salicylic acid or aspirin. It's interesting because it has this ester and this carboxylic acid attached to it. And it's related to a few other compounds. Of course, yeah, this is aspirin. And you can take it for pain. It's a non-steroidal anti-inflammatory drug. But it's structurally related to some other compounds that you can get from nature and that actually were used even before people knew what aspirin was to treat pain. So this is the alcohol version of this ester. Do you see the common structure? Sort of, yeah? Yes? Yes, I did press record, but thank you for the reminder. And audio is being captured, so we're good to go. This is called salicylic acid. It's actually used in some skincare and products for various purposes, but it's also a painkiller. You can isolate it from a plant called meadowsweet, and another plant, willow bark, contains a compound that's also structurally related, but not quite the same. This is from your text, actually. This 6-membered ring is actually probably glucose, but we're not showing the stereochemistry because sometimes we don't do that when we're in a hurry. And this is called salicin, and they all have this same sort of core structure of a benzene ring, an oxygen, and a carbon. Up here, it's an alcohol and an OR group, but that's sort of the same core structure. Aspirin was a great molecule because it can be formulated in pill form and you can swallow it. Before, you could get salicylic acid and most often it would be isolated as the conjugate base. This is called sodium salicylate, and it's cloyingly sweet. Like you could put it in your mouth and it would be so sweet that actually patients couldn't tolerate it very well. It made them sick. So making the ester actually made a big difference there. There also are some other acids that are important while we're on the subject of pain. There are a few derivatives of a very long chain acid called arachidonic acid, which I'll draw for you here. I know that some of you don't believe me when I say that I will not ask you to memorize this structure, but I promise not to ask you to memorize this structure. But it's a 20-carbon acid, and it's a precursor and can be cyclized to form via a molecule called cyclooxygenase. This is an enzyme in biochemistry that you'll learn some stuff about. it can be cyclized to form some other molecules which are called prostaglandins. And these are involved, there are many of these, and they're involved in pain and inflammation. I will draw just one of them, mostly to show you the horror of what biology can do. There's a lot of stereocenters in this molecule. Horror, actually, most organic chemists call it beauty. They love what biology can do in generating these complicated structures. There's the carboxylic acid that's present. And then we can draw the rest of the molecule without a whole lot of effort. Maybe I'll just put an R group there and we'll call that good. That's prostaglandin F2 alpha. And again, these are involved in pain and inflammation. The stories are related because aspirin blocks and inhibits the effect of cyclooxygenase, and so lowers the amount of prostaglandins that are involved in pain and inflammation. Prostaglandins are all locally synthesized near the site of inflammation, so if you stop it from happening, then you can stop the symptoms of pain and so on. Okay, so what are you supposed to get from that? I don't know, but some of you aspire to prescribe drugs that people take, so you probably should also aspire to be at least curious about what those drugs are and what they do. All right, let's talk a little bit about carboxylic acids and acidity. This may be a bit of a review from stuff you learned in 351. That's okay. We rationalize acidity by considering the stability of the conjugate base. So, for example, it is no surprise at all that if we look at pKa's, the carboxylic acid, like acetic acid, generally has a pKa in the 4 to 5 range, whereas an alcohol has a pK of 16, and we rationalize that by looking at the ability of the conjugate base to handle the negative charge that's left behind when the proton gets removed. Of course, you can see that the carboxylic acid is resonance stabilized, that negative charge is delocalized on both of those oxygens. And that's worth a factor of 1 trillion in acidity compared relative to the alcohol. That should be reviewed, shouldn't be any necessarily new revelation there. But it turns out that there are things that we can add to a carboxylic acid that will modify its acidity, and these are called inductive effects. You've seen this too, I think, in 351, but we'll review it here. As an example, if we add a single chloro group on the alpha carbon of acetic acid, we get chloroacetic acid, and its pKa is more than a log unit lower, so 10 times more acidic than acetic acid. The rationale for that is the presence of the chloro, that electronegative group at the alpha carbon, tends to pull electron density away from the alpha carbon, which then pulls electron density away from the carbonyl carbon, which then pulls electron density away from those negatively charged oxygens. This sort of tug of war of electrons in sigma bonds due to electronegativity differences is called an inductive effect. And that can increase the acidity of a carboxylic acid. If you add more chloro groups, for example, the trichloroacetic acid, well, let's do both. The dichloroacetic acid has a pKa of 1.3, and then if you put 3 of them on there, the pKa drops down even further to 0.9, much more acidic. And trends follow in much the same way as you would expect. If you do fluoroacetic acid instead of chloro, the pKa is a little bit lower, meaning fluoroacetic acid is more acidic. That should be obvious because fluoro is more electronegative than chloro, right? And so it makes sense that it would be better at pulling electron density away via an inductive effect. I'll point out that these inductive effects are highly local, and so you might expect that the further you move the chloro away, the less difference it makes. So we'll just compare briefly, what if we move the chloro instead of, well, we'll compare the following series of 4 carbon carboxylic acids. And let's put the chloro on the alpha carbon. That's a 1, 2, 3, 4 carbon. 1, 2, 3, 4. Yep, on the alpha carbon versus the beta carbon versus the gamma carbon. That's not an R, that's a Greek letter gamma for penmanship. It turns out that on the alpha carbon, the acidity is again around 2.9 in pKa. At the beta carbon, it goes back to being about the same as expected for a carboxylic acid, and on the gamma carbon, again, about the same. So the impact of nearby electronegative groups is mostly just for those that are on the alpha carbon relative to the carboxylic acid. Beyond that, not such a big deal. Questions about that? Yeah?
So is that electron drawing?
Yes, that's electron withdrawing by the chloro groups, yes.
What would be an example of like electron donating?
What would be an example of an electron donating group in this case? You would want something that is more electronegative, or rather less electronegative than carbon. And so that would sort of be, I would have a difficult time coming up with an example. Let me see real quick if I can find one. Not off the top of my head, sorry. Well, not exactly. You asked. We were going to do this later anyway, but inductive effects, as I've said, tend to fall off with distance unless conjugation is involved. So I'm going to show you some, I wish I had pKa numbers in front of me, but I don't. So we'll just have to go qualitative. There are a class of carboxylic acids called benzoic acids. This is where the carbonyl carbon of the carboxylic acid is attached to a benzene ring. So this is just the straight up benzoic acid, okay? And depending on what groups you put on the benzene ring, you can change the acidity of the carboxylic acid. For example, and we'll have more to say about some of these ideas later. I'm just going to touch on it briefly now. This is paramethyl benzoic acid. You don't need to know the name. This is actually going to be less acidic. And in contrast, parachlorobenzoic acid is going to be more acidic. And the reason for this, basically, it's a little complicated, but we can reason it through this way. First, understand that a benzene ring is composed of sp2 hybridized carbons, which are more electronegative than sp3 hybridized carbons. And so you might imagine that this benzene ring itself could be pulling electron density away from the carbonyl carbon. If we make the benzene ring more electron rich, what do you predict that's going to do to the acidity of the carboxylic acid? And we'll rationalize that by thinking about the stability of the conjugate base. If the benzene ring is electron rich, what should that do to the carboxylic acid? More acidic or less acidic? Less acidic. Good. Why? Go ahead. Sure, in the conjugate base, you already have extra electron density there. The more rich the benzoic acid is in electrons, the more it's going to repel slash destabilize the negatively charged carboxylate group. In contrast, if the benzoic acid, if the benzene ring is electron poor, that will, via an inductive effect, suck electron density away from the carboxylic acid, make the conjugate base more stable. So that's what's going on here with para-chlorobenzoic acid. The chloro makes the benzene ring more electron poor via just electronegativity, and then that electron poor benzene ring, via an inductive effect, withdraws electron density away from the negatively charged carboxylate, making the carboxylate, the conjugate base, more stable, and therefore the acid more acidic. Yeah? Go ahead.
So why is the one in the middle more acidic than the one on the right? If the right one has a CH3 attached.
Right, so what about the comparison of benzoic acid in the middle with the paramethyl version? It turns out that alkyl groups on benzene rings, because of the difference in hybridization, sp3 carbons have less S character. That means they're actually less electronegative than sp2 carbons. It's something that you probably heard before but maybe forgot. sp2 carbons are more electronegative than sp3 carbons. So the more alkyl groups you have on a benzene ring, the more electron rich the benzene ring is, because those sp2 carbons in the ring will actually pull electron density away from the alkyl groups. So alkyl groups are examples of what we will call inductive electron donating groups. They tend to make the benzene ring more electron rich, and that then destabilizes the conjugate base, making the corresponding acid less acidic. Yeah?
If there would be like two chlorines on the beta carbon, but then like one chlorine on the alpha carbon, we'd be expected to know the difference, like which one would be more acidic.
Oh, now you want to mix and match. You're like, okay, what if we do this versus that?
Yeah.
Probably somebody knows the answer, but I don't. Okay, what else? Yeah.
Does this same effect happen, not necessarily on like a benzene ring, but in just a hydrocarbon that has like an electronegative chlorine or chlorine atom? Like say if I have another electron-rich group on the other side of that same of that electronegative atom, is the same effect happening to an extent, or is it really only with like a benzene ring on the scene?
Well, maybe I'm not sure I understand your question. What I guess I meant to communicate by the benzene ring is the fact that I'm counting alpha, beta, gamma, delta. For benzene rings, substituents on the delta carbon make a difference. They don't as much for a regular hydrocarbon chain. And presumably, the reason for that is the benzene ring and its unique electronics, which we're going to talk about, but we haven't yet. Yeah?
So the delta carbon is the most influential spot out of electron photography?
Not necessarily. That's just what I've chosen. We could have put it closer and it would have made similar differences. And yeah, as you would predict, there's a whole actually area of what's called physical organic chemistry that's really interested in, well, what if I put the methyl group here? Or what if I put it there? And there are some things to learn there. Some of them we will get to, others we won't, but I'll just sort of punt for the future chapter. Okay, yeah?
So when the ring is like drawing electrons away from the carboxylic acid, that makes it more or less stable?
When the ring withdraws electron density from the carboxylate group, that makes it more stable. That makes the carboxylate conjugate base more stable, and the acid correspondingly more acidic. That which makes a conjugate base more stable also makes the acid more acidic. Okay. What I want to get to is something that's covered that if you had 351 from me, you probably heard before. If you didn't, this may be your first time through. And that is how to use pKa information along with pH to determine whether a group should have its proton still or not in biological settings. Before we do that, though, I need to introduce you to the cousin, the biological cousin of the carboxylic acid, and that is phosphoric acid and its various derivatives. So your text calls this acids that contain phosphorus. And you should get used to these because you're going to see them all over the place. Acids that contain phosphorus. What I need is an AI-empowered iPad that writes words that I'm saying, but only the ones I want to write while I'm saying them, and keeps up with me. All right, so we're going to introduce this by actually reintroducing you to an old friend, which was H3PO4, or phosphoric acid. You met this acid in Gen Chem, and you hated it because it had 3 potential acidic protons. And probably in your nightmares, you still have the time where somebody tells you, how much of monosodium phosphate should I mix with disodium phosphate to get a 1 molar buffer that has a pH of 7.35892? And please use correct significant figures, right? Take a minute, take a deep breath. You got to recover from that traumatic experience. Don't worry, we're not going to do that. The bad man has gone away, right? There's a new order. We are going to talk about pKa's though, and we're going to use that information to have some intuition about what's going to happen. So there's phosphoric acid. The pKa of the first proton there is 2.2. 1 significant figure is good enough. The conjugate base of H3PO4, you will recall, is the monoanion. Monoanion. And it also has an acidic proton. Those 2 OH groups are identical, so don't get distracted by the fact that I only highlighted one of them. Its pKa is much higher, 7.2. The rationale for that you learned in general chemistry is that it's harder to lose the second proton because the conjugate base of the monoion has 2 negative charges instead of 1. And so there's some charge-charge repulsion. So here's the dianion. This would have been disodium phosphate. And it also has an acidic proton, but that proton has a much higher pKa of 12.3. And then you have the fully deprotonated conjugate base here. And this brings together, this is a polyprotic acid, and then it's also a polyatomic anion. I had a son who's currently on a mission in Kentucky who remembers the horrors of polyatomic ions and how terrible that was in general chemistry. Okay. So we're going to talk about how to know, as a function of pH, which of these is the major species, which is the one that's going to dominate. And it's going to be way easier than you think. But I want to show you some related biological molecules, and we're going to actually use these numbers to sort of predict what the pKa's should be. For example, one of the first intermediates in the metabolic pathway known as glycolysis involves something that you will later call glucose 6-phosphate, which I'm drawing for you here. And this functional group here is called a phosphoester. It is similar in stability to a regular ester, and it's got 2 acidic protons. The first one should have a pKa that is similar to the first pKa of phosphoric acid, because that first proton would involve going from a neutral species to the monoanion. Okay? Those of you who are writing with pen and paper are now hating what I'm doing, and I don't care. Copy and paste. That's the monoanion, and then the second pKa you predict to be close to 7.2, and then again, sorry, But I'll make the notes available to you, so you don't have to worry about scrambling to get it all down. And then you'd have the dianion, right? And we could similarly ask the question, which do we expect for this phosphoester? Should it be neutral? Should it be the monoanion? Should it be the dianion? Similarly, you'll encounter nucleoside triphosphates. So this is a fun one. Get ready to scramble along. Can you write it as fast as me? Oops. So this is going to be the structure of ATP. Here is the ribose ring. If you want, you can just abbreviate, starting with the nitrogen, abbreviate A, and we'll get there later on in the semester, so don't worry too much. I'm actually not sure I can do it right myself without looking it up. I think this is ATP. Notice that ATP has a number of different acidic protons. And so predicting, you're not going to necessarily need to be worried about that, but you would expect the first one to come off to have a pKa around 2 and the next one to be around 7. Which one comes off first probably doesn't matter, and in fact it gets more complicated than that, because what happens in a lot of cases in biology is these nucleoside triphosphates are accompanied by divalent cations that can neutralize the conjugate base. Right? So now the conjugate base doesn't just have a negative charge, it's paired with a corresponding complementary anion. And that can do things like make it really, really easy to lose a couple of protons so that you end up with something like this instead, where there's an ionic interaction between these negatively charged phosphate groups and magnesium. I'm not really expecting you to predict pKa's for something like this. I certainly can't do it. But I do, when you see phosphate groups in biology, I do need you to be thinking the first one's probably pretty acidic, more acidic than a carboxylic acid. The next one after that probably has a pKa of around 7. The last place that this tends to show up is in DNA. You guys are used to thinking about, or have seen in other classes, DNA has a quote-unquote sugar phosphate backbone. So this is one sugar and this is the other sugar. And you expect the pKa of this proton on DNA, or RNA for that matter, to be around, again, 2.2. And we will later learn that that means that physiological, why are we drawing in pink? It's lovely, but that means we will later learn that at physiological pH, that proton is gone and the backbone of DNA is negatively charged. Okay? Being able to look at a functional group and say, okay, if the pH is physiological, what should that group be? Should it be negative, neutral, positive? That's actually really useful for biochemistry. It can save you from making embarrassing mistakes as you're thinking about biochemical reaction mechanisms, as you're thinking about protein and nucleic acid structure. So now I'm going to show you how. And to do that, we're going to resurrect another demon from your past, the so-called Henderson-Hasselbalch equation. Okay. Those of you needing to dry heave, there are trash cans somewhere. Boo, Henderson-Hasselbalch equation. I'm going to show you what organic chemists use this for. It actually has diverse uses. You used it in your general chemistry days to make buffers, basically. If I want the pH to be 7.2, how much of monosodium phosphate versus disodium phosphate do I need to mix together? And all of that's fine. We use it much more intuitively in organic chemistry, and I'll show you how that works. So rather than memorize the equation, let's set up in equilibrium a generic acid with water. And water steals the proton, and then you've got the conjugate base. That should look really familiar to you from 351. This is actually what they meant in Gen Chem when they talked about acid dissociation anyway. if we were to write the equilibrium constant as expressed here, it would be the concentration of hydronium times the concentration of conjugate base over the concentration of HA times the concentration of water. Now, water is about 55 molar at regular temperatures and pressures. And it doesn't, that concentration is usually vastly in excess of whatever salts or buffers you have in an aqueous solution. So usually that concentration of water remains constant. So hopefully you can forgive me, we're going to multiply both sides by the concentration of water, making a little bit more space for ourselves. And then what's over on the left-hand side of the equation is our new constant, which we call Ka. That's right, pKa. This is our acid dissociation constant. And it sort of combines two things, the concentration of water and the equilibrium constant. Now, you've seen before how we get pKa, right? We take the minus log of both sides. I promise you this is as bad as the math gets in this class. Okay, now you have to dig way back in your memory and remember something about properties of logarithms. Ugh. Do you remember that the log of A times B is equal to the log of A plus the log of B? It's true whether or not you care anymore. We're going to use that along with the definition that pH equals minus log of hydronium concentration to rewrite this equation as follows. pKa equals pH plus, still minus log of whatever's left in that quantity. See what we did there? We just used properties of logarithms to separate out the log of the hydronium concentration. Okay, now we can rearrange this any way we wish. One of the most easiest ways to do this is pKa minus pH equals minus log of conjugate base over acid. And then another property of logarithms is, suppose I don't like the negative sign there, I can just make that equal to the positive log of acid over conjugate base. So that's the form, and I'm not sure totally how it's written in your text. It might have been rearranged in another form that you maybe have seen in other places. What this does is it says if we know what the pKa of a given acid is, and we know what the pH of the solution is, we can tell how much of that acid should be in its acid form versus its conjugate base form. All of this really relies on the assumption that we're doing this in dilute aqueous solution where the pH is held constant. Fortunately, that is the context for biology. Right? In biology, pH is held pretty constant. There's some subcellular organelles where it's a little bit more acidic, as in there's endosomal acidification. The lumen of your stomach is quite acidic, but for the most part, your blood, the interior of your cells, around 7.2, 7.4 pH. So that's held constant, and it's buffered, and that pH controls the protonation state of the acids that are dissolved in that buffer. So let's do an example. Let's take the phosphoester in glucose 6-phosphate, and let's suppose that, let's say we are in blood, so pH is 7.4, okay? We're going to make this comparison one by one for these two equilibria. The pKa for the first acid is 2.2. The pKa for the second is 7.2. Just zooming in on the first one and remembering what we've learned above for the Henderson-Hasselbalch equation. Compare the pKa of 2 to the pH of 7. 2 minus 7 is a negative number or a positive number? Negative, good. We're all in agreement. Negative number. Okay. Now, property of logarithms. If this number is negative, what does that tell you about these two numbers? Which one's bigger than the other? Okay, if the number is negative, then the number inside the log has to be less than 1. Numbers greater than 1 have a positive logarithm. Numbers less than 1, between 1 and 0, have a negative logarithm. So if the conjugate base is in greater conjugate concentration than the acid, this log has to be negative. Some people like thinking about the math that way. Other people prefer words. I've said this before in classes in 351. People are like, wait, say that again? Then they repeat it back to me wrong. Then I say it to them again. And then they're like, okay, whatever you got to do to figure it out and remember it, go ahead and do. But if my pKa is less than the pH, then the conjugate base form dominates, meaning that proton is gone. Okay? So, if pH is 7, the pink proton, pKa 2, there or not there? Not there, gone. Where is it? It turned into hydronium somewhere. Okay? Okay, now let's look at the second number, which is 7.2. pKa of 7.2 minus pH of 7.4. That number is still negative, but only slightly. Let me ask you this. If pKa is equal to pH, what does that tell me about the ratio of acid to base, conjugate base? Equals 1, right? Because the logarithm of 1 is 0. Right? So when pH, let's formulate this in words. When pH equals pKa, concentration of acid equals concentration of conjugate base. We're sort of at the 1-on-1, 1-to-1 ratio. When pKa is greater than pH versus when pKa is less than pH. When pKa is less than pH, that means that the base form dominates over the acid form. When pKa is greater than pH, that tells you that the acid form still dominates. Okay? So, what does that tell you? What do I expect for glucose 6-phosphate? Should it be the neutral species, the monoanion, or the dianion? Slightly excess, certainly no neutral species, slight excess of dianion. Which means if you want to draw glucose 6-phosphate, you are free to draw it, and you want to draw it at physiological pH, you're free to draw it as the monoanion or the dianion. Most people will draw it as the dianion, but that doesn't, because it dominates, but not by much, as you can see. Okay? Now, you can use this for much larger groups, and if you took 351 from me, you will have some harrowing memories of this kind of thing. So let's go ahead and bring those back, shall we? Like an army of inferi conjugated by, or conjured by the Dark Lord in Book 6 of Harry Potter. Is that a spoiler for anybody? My 13-year-old is reading The Half-Blood Prince, and one of his older brothers told him that Snape was the Half-Blood Prince, and then he got mad because it was a spoiler. We're like, buddy, we're almost 20 years on now, so I think probably, anyway. It's hard not to let things slip, but also, Anakin Skywalker became Darth Vader, and he is Luke Skywalker's father. I hate to tell you this, but oh. All right. So what I'm going to do is draw for you some side chains on a protein. We're going to learn about amino acids, and we're going to learn about side chains of amino acids. We're going to learn about peptides and proteins in a future chapter. But already you should have sufficient skills to answer this question. In fact, many of you probably had these skills in 351. or thought you did and then got a problem wrong on an exam. And so now's your chance to try again. I'm showing you various protein side chains in their fully protonated forms. And I will write down the associated pKa's for each of these side chains. So this one here happens to be called lysine. It has a pKa of 11. This one here happens to be called glutamic acid, and it has a pKa of 4-ish. This one is called tyrosine, and it has a pKa of around 10. And maybe we should highlight the protons that we're talking about. Notice that some of these acids are neutral, and they lose a proton to form a negatively charged conjugate base. Those are the ones that are easiest to follow and understand. Some of these are positively charged. They're positively charged acids with neutral conjugate bases. And often students forget about those, especially if I draw the peptide or the molecule in its neutral form. So be sure to look for positively charged conjugate acids of neutral bases. This is called an ammonium group. What we've got over here is a neutral thiol, and its pKa is around 8. This is called imidazolium. Not that you need to know that unless you want to try to bust that out to impress people at parties. If you do that, try to have it be a party where there are a lot of organic chemists. We are suckers for people that can bust out names of what we call heterocycles. These are molecules that have oxygens and nitrogens in rings. So oxazolidinone makes us swoon a little bit. So if you could pick up some of these words. Anyway, this one's called a guanidinium. Sorry, I guess that went a little too far. Sorry, I'll just... Okay. This one over here is called guanidinium, and this is from the arginine side chain. If you've heard of histidine, that's what this is. In any case, with these pKa numbers, you should now be able, as a function of pH, to tell me what form these should exist in, their current acidic forms or their corresponding conjugate bases. To answer this question, it's actually helpful if you go ahead and draw what the neutral conjugate base is, or in the case of the carboxylic acid, what the negatively charged conjugate base is. I'll do that real briefly just so that we are clear on what we're talking about when we consider these various acids versus their conjugate bases. When you don't have the positive charge on that nitrogen, that 5-membered ring nitrogen, it's actually just called imidazole instead of imidazolium. And when you don't have the positive charge on the neutral, on the nitrogen for the conjugate base of the guanidinium, it's just called guanidine. That doesn't matter too much. All right, so let's go through as a function of pH. Let's have pH equal 7. We're going to highlight that in orange, and we're going to color in whether it's the acid form or the conjugate base form that dominates as a function of pH. So you tell me, starting with the ammonium ion, pKa 11, at pH 7, is that proton still there or gone? Still there. Lysine side chains are positive at physiological pH. That's an important conclusion for biochemistry. How about the carboxylic acid? Proton still there or gone? pK of 4. Gone at pH 7. Carboxylic acids like glutamic acid and aspartic acid are negatively charged. That can have consequences because plus charges and negative charges can interact favorably. How about this functional group? It's called a phenol. It's the tyrosine side chain at pH 7. Still there or gone? Still there. Still there, like the Energizer Bunny. Is that still a thing? That was a commercial when I still saw an Energizer Bunny commercial. All right, thank you. pH 7, is the thiol proton still there? Yep, still there. pKa greater than pH. How about guanidinium? pKa of 12, I didn't write down. Still there or gone? Still there. And imidazolium, pKa I didn't write for you, is 6. Still there or gone? Gone. Good. So now that's what you have to do to even answer the question. Now the question usually becomes, what's the overall formal charge on this molecule? So you got to get all of those answers right, and then you have to be able to count all the pluses and subtract all the minuses. So if we do that, there's a plus there, a plus here, and a minus there. So overall, the charge would be just +1, right? So that's the kind of thing I'm going to expect you to be able to do moving forward. Now, you'll have all this pKa information, so from that perspective, it's not such a huge deal, but you're going to have to go through and sensibly make those conclusions using the Henderson-Hasselbalch equation. Okay, yes?
So, if pH is different than the pKa, both molecules still exist, right?
Right. If the pKa and the pH are different, or in all of these cases, both the acid and its conjugate base are in equilibrium. So we're really talking here about what is the major dominant form. Yeah, other questions? Yeah? Okay, I'm not sure I understand your question. I guess one way of restating that would be yes, if pH were higher than 11, would the proton fall off? Yes. But that's not what you were asking?
No, it's like if it's lacking an electron versus a proton, we get one.
Okay, yeah, good question. And I think this question comes from someone who has had, I think this question reflects how I actually ask these questions in an exam. So what I will do often to really test your knowledge of this is instead of drawing the molecule in whatever, instead of drawing the molecule in its fully acidic form, I will draw it in its neutral form. This is difficult for students to understand because they only, at this point, most students that haven't practiced a lot will look at that and say, okay, they'll just focus on losing protons versus gaining protons. But what you have to understand is that when you dissolve a molecule in dilute aqueous solution that's buffered, there is plenty of H3O plus and OH minus to give protons and to take them away. So when you see a neutral molecule like this, you should be thinking about the possibility that it could gain a proton from the H3O plus that's in solution, and that process has a pKa of 11. You could also be concerned that it might lose a proton to form the negatively charged amide anion, though a quick looking up of that pKa tells you not to worry about it. Why? Anybody? Why am I not worried about the neutral amine losing a proton at pH 7? Because 38 is a gazillion times bigger than 7. Well, not exactly a gazillion. But in log units, it basically is. That tells you that never in the history of the universe has a neutral amine lost a proton to water. Okay, I think that's enough for today. I'll see you Friday. Have a happy Wednesday.